Today we're reinventing voxel ray traversal from scratch to be able to render over 32 billion voxels in real time. Most voxel games, like Minecraft, convert their worlds into triangle meshes to render them. To me, this has always felt like a compromise. We waste time, memory, and complexity converting perfectly good voxel data into triangles because GPUs are optimized for triangle rasterization. But what if we could render the world directly? No triangles, no meshing, and somehow do it fast enough for real time. That's exactly what we'll do today. We'll go from the basics of what a voxel even is to an algorithm capable of rendering billions of voxels in real time by casting a ray for each pixel on the screen using the GPU. And towards the end, I'll show you one simple optimization technique that 10x'd the FPS. So, how do we go from a bunch of voxels and a camera to pixels on a screen? Well, to answer that, we need to start at the very beginning. What is a voxel? The screen you're watching this video on is made up of millions of physical pixels, behind each of which is a logical pixel, a simple piece of data that determines its color. This is often an RGB color, but it doesn't have to be. It could just as well be a single luminance value, or literally anything else, and it would still be a pixel. In my opinion, the only thing required for something to be a pixel is that it's a small building block of 2D space. In the same way, we can imagine 3D space as being made up of so-called voxels. For simplicity, my voxels will each be a single bit of data. On or off, 1 or 0, true or false, solid or empty. But like pixels, voxels can store any kind of data you want. For example, each voxel could hold an integer representing a material type like air, stone, grass, dirt, etc., etc. But the idea of a grid of voxels itself doesn't help us a lot unless we can efficiently read and write it to memory. Therefore, we'll use this flattening function to convert a 3D coordinate to a 1D index, allowing us to store the voxel data in an array of size width times depth times height. You can think of this function as taking each layer along the y-axis and placing them side by side along the x-axis, and then taking each row along the z-axis and placing them end to end. There are other methods that preserve spatial locality better to improve memory performance, or ones that compress the voxel data to use less memory overall, but I'll talk more about those towards the end of the video. Going forward, the visualizations will be in 2D, and the math and algorithms will be in 3D, but all of it works in any dimension you want, with only a few minor modifications. Finally, we need to be able to convert an arbitrary position in space to the corresponding voxel coordinate, and for that, we'll just take the floor of each component. If this position has the possibility of being outside of the grid, due to numerical errors or actually being outside, we'll have to clamp it or check it to make sure we don't access out of bounds. Now that we know what a voxel is, how do we describe the idea of a pixel looking at one? That's where the mathematical concept of a ray comes in, which leads us to the next question. What is a ray? In our case, it will make the most sense to define a ray given by the origin O and the non-zero direction D as the set of all points P that satisfy these two constraints. In other words, all points from the given origin along the given direction. The variable t is a parameter that tells us how many multiples of the direction we've moved from the origin. Note that nowhere in this definition do we say that the direction is normalized. It can be whatever length you want, as long as it's not 0. So, given a ray corresponding to some pixel, we need to figure out if it hits a voxel, and if so, which one. The idea is to walk through the voxel grid in increasing values of t until we either find the first solid one or exit the bounds of the grid. This is what's known as voxel ray traversal. Now that we know the idea behind what voxel ray traversal is, we can start to think about how we would implement it. Let's begin with the naive method, because every good computer science problem starts with something painfully slow and completely wrong. In this case, that would be to just start at the ray origin, stepping forward in small delta t multiples of the direction, checking for a solid voxel at each step. This works, but it has one major issue. It can completely miss voxels which the ray should intersect with. And if we try to minimize the risk of this by decreasing the step size, we could spend hundreds or thousands of iterations on a single voxel, which is very slow, not to mention that it doesn't even fix the issue. So let's take a step back and think about the problem again. We have a grid and a ray, and we want to determine which voxels the ray intersects with in order. So let's start simple. How do we find the first voxel? If the origin is inside of the grid, we know that the first voxel is just the floor of the ray origin. But if it's outside, we somehow need to calculate where the ray enters the axis-aligned bounding box around the grid. For this, we'll need a ray AABB intersection algorithm. To do this, we will take the mathematical definition of a ray and the mathematical definition of an AABB and solve for the ray parameter t. After working through the math and handling some edge cases, we arrive at this algorithm, known as the slab method for ray AABB intersection. Now, because it's almost always faster to multiply than to divide, it makes sense to pre-compute 1 over the direction and store that in our ray struct, and then multiply by that instead of divide by the direction. From the ray AABB intersection algorithm, we get the values of t when the ray enters and exits the bounding box. If we don't hit the bounding box, we know that we won't hit a single voxel in the grid either, so we can return early. Otherwise, we use the first t value with the ray definition to calculate the point of entry. Since this point has the chance of being slightly outside of the grid due to floating point errors, we'll need to use the clamping version when we get the corresponding voxel coordinate. Now that we know how to get the first voxel that the ray intersects with, the only thing we need for a complete voxel ray traversal algorithm is a way to get the next voxel, since then we can just do that in a loop until we hit a solid voxel or go out of bounds. So, given a ray, which we know intersects with a given voxel, how do we find the next voxel that the ray intersects with? Well, we can imagine the voxel grid as being made up of a stack of axis-aligned planes along each axis. The ray travels through these planes, and whenever it crosses one of them, we enter a new voxel. So to find the next voxel, all we need to do is figure out which of these planes the ray will exit the voxel through. The lesser plane on each axis just has the positions of the components of v, and the greater planes the components of v plus 1. First of all, we can notice that if the x component of the direction is positive, we can never exit through the lesser x-plane, and if it's negative, we can never exit through the greater x-plane. This applies to y and z too, which brings us down to one plane per axis, which we can determine the positions of based on the sign of the direction. Because of some quirks of floating point 0, we'll actually want to use the sign of the inverse of the direction instead of the sign of the direction directly. Now that we know the position of the planes, we just need to calculate which plane the ray intersects with first. So let's focus on the x-plane. Since the x-plane is defined as all points for which the x-coordinate is a certain value, let's call it x0, and the ray is defined as all points that satisfy this equation, we just have to solve for the value of t when the x-component of p is equal to x0. This is just a linear equation, and by solving it, we get this. And I'll call it tx because it's the t value to hit the x-plane. Of course, we could just as well have done this for the y-axis or the z-axis, and the derivation would have been the same. Now that we have the three t values, we just have to compare them to see which one occurs first. From the sign of the direction, we also know if we're supposed to step in the positive or negative direction. In other words, to get the next voxel in the traversal, we want to add the sign of the direction to the component of the voxel coordinate for which the plane intersection t value is lowest. And again, for the same reason, we'll use the sign of the inverse instead. Putting it all together, we first calculate the initial voxel using the ray AABB intersection algorithm. Then, we repeatedly step to the next voxel by comparing the t values for the plane intersections. And if we continue this process until we hit a solid voxel or exit the bounds of the grid, we will have traversed every intersected voxel. One quick improvement. We can see that each iteration chord is increased by the sign of the direction, which means that t is increased by the sign of direction times the inverse of direction, in other words, the absolute value of the inverse of the direction. Therefore, we can pull out the entirety of t and increment it each iteration instead. The algorithm that we now have is essentially the one described by Amanatides and Woo in their 1987 paper, A Fast Voxel Traversal Algorithm for Ray Tracing. Now let's use this algorithm to render something. And for that, we of course need something to render. Therefore, I have chosen the Stanford Bunny, a model which is very popular in computer graphics. The Stanford Bunny is a triangle mesh, so we'll need to voxelize it, which I won't cover how to do in this video, but the algorithm is included in the GitHub repository in the description below, along with a bare-bones implementation of this video's topic in Rust and Vulkan. And now, if we set up a camera and shoot a ray for each pixel using a compute shader running the algorithm, we get this. Right now, the traversal only tells us if we miss or which voxel we hit. But with a bit of extra math, we can efficiently calculate which face of the voxel we hit, where on the face we hit, and how far from the camera it happened. This gives us everything we need for basic shading and texturing, or even launching secondary rays for ray tracing. Now it's time for that one optimization that I alluded to at the start of the video. Currently, at a grid resolution of 2048 cubed and a screen resolution of 1000 by 1000, we're getting about 12 FPS. After this optimization, we'll hit roughly 121 FPS, which is a 10x speedup. But before we get to that, I want to cover an alternative optimization which is almost as good, but way easier to explain. In the What is a Voxel section of this video, we covered the flattening function, and I mentioned that there are other ways of doing it. It turns out that if we switch to this one, known as a z-order curve, we get 102 FPS, which is already over 8 times faster. You might be thinking, wait, we just made the flattening function way more complicated, and it got faster? Yeah. The reason why is that with a z-order curve, we place voxels that are nearby in space, nearby in memory. This has two main implications on the GPU. First of all, since our voxel ray traversal always steps from one voxel to a neighboring one, this improves the likelihood that the next voxel is already in the cache. And second of all, it improves the likelihood that two nearby rays want to access the same memory, meaning that the GPU doesn't have to read as much data into cache. All in all, this means we spend less time waiting for memory to read, and more time actually traversing. Now, like I said before, there's actually a better way to do this. Since we're doing the traversal on the GPU, we have access to GPU-specific structures like 3D textures, which are heavily optimized for data locality using way more sophisticated methods than just z-order curves. Switching to storing our voxels in a 3D image brings us to 121 FPS, which is a 10 times improvement over the original 12. So by rethinking how the voxel data is stored in memory, first with a z-order curve and then a 3D texture, we brought our FPS from 12 to 121 without even changing the algorithm itself. So there you have it. From the definitions of voxels, rays, and traversals to a complete real-time rendering pipeline with 0 triangles, capable of rendering billions of voxels. Of course, this is nowhere close to an end-all be-all. There are huge improvement possibilities to both the data structure and the algorithm. For example, what if we could compress the data so that more voxels can fit in less memory? Or what if we knew that larger regions of the grid were completely empty, meaning that we could step through them in their entirety all in one single iteration? But I'll leave that for the next video, where I'll be covering sparse voxel octrees and an improved voxel ray traversal algorithm that takes advantage of the sparseness. Thank you for watching, and till next time, goodbye.